To illustrate the concept of integration and specifically dealing with the area underneath the curve, we are going to consider the curve y equals x squared. Specifically, we're going to focus on the points 0, 0 and 1, 1 that lie on the curve. So we are going to be looking at the area underneath the curve between the 2 points. So we've drawn 5 rectangles underneath the curve between the points 0, 0 and 1, 1. Now, it's not a very good approximation. If we calculate the area of each of these rectangles and sum them, you'll get an approximation of the area underneath the curve between the points 0, 0 and 1, 1. But it's not a very good approximation because you've got this white space at the top of each rectangle and underneath the curve, which is a lot of white space. The area above the rectangles and beneath the curve is space that is not included in the area of the rectangles, right? So if we sum the area of each of these rectangles, we'll only get a rough approximation of the area between the points 0, 0 and 1, 1 underneath the curve, but it's not a very good approximation because we've got so few rectangles. So to overcome this, to get a better approximation, we will increase the number of rectangles between the 2 points. And as we increase the number of rectangles, we're getting a far better approximation of the area underneath the curve between the points 0, 0 and 1, 1. So at this point, we have got 50 rectangles underneath the curve. And if we continue increasing the number of rectangles, we'll get a far better approximation of the area underneath the curve. We are now at 100 rectangles. If we move up to 150, it's an even better approximation. 250, we can't even see the rectangles anymore. We're at 500 now and 1,000. So it's completely indistinguishable. We cannot possibly see with the naked eye how many rectangles we've got there. We've got 1,000, but you wouldn't know that just by looking at it. So if you look at the shaded area now, it almost exactly fits the area underneath the curve. So what this illustrates is as the number of rectangles increases, and we increase the rectangles to infinity, ad infinitum, so as the number of rectangles increase, we get a far better approximation of the area underneath the curve between those 2 points. Now, since we can't measure infinity, if we take the limit as n approaches infinity, n being the number of rectangles underneath the curve, so as we take the limit as n approaches infinity, we get the exact area underneath the curve. And that is how integration was born. So that is the entire crux of integration and the area underneath the curve. If we continue increasing the number of rectangles ad infinitum, then it's safe to say that the area underneath the curve between the points 0, 0 and 1, 1 will approach a third. You can clearly see as we increased from 150 rectangles where the area was 0.33 to 1,000 rectangles, the area is 0.3328. And these are approximations, they're rounded to 4 decimal places. But it's safe to assume that it would reach a limit of a third. So in other words, as the number of rectangles approaches infinity, then the area would approach a value of a third. And you can actually show this by using integration. And this is the whole crux. This entire area underneath the curve is how integration was born. Integration has a symbol which is an elongated S. That's the reason why we have this symbol, is because we are summing the areas of the rectangles, infinite number of rectangles underneath the curve. So we are dealing with the limit as n approaches infinity of the area, which we'll just denote with an x right now, and this equals a limit. In this case, that limit would be a third. And this is the whole crux and idea behind integration. You can also estimate the area underneath a curve by drawing in rectangles that overlap the curve, as is illustrated. If we take a point, xi, f of xi, then the height of the rectangle will be f of xi, and the width of the rectangle will be the difference between xi and the point directly before it, x sub I minus 1, which is the change in x, in other words, delta x. So f of x sub I will be the height of the rectangle, and delta x is the width of the rectangle. And the area of a rectangle is width times height, or length times breadth, however you want to look at it. So the area of the ith rectangle will be f of x sub I times delta x. Now, as the number of rectangles increase, the difference between x values, in other words, the delta x, which is the width of the rectangle, gets smaller and smaller and smaller. So as the number of rectangles increase to infinity, that delta x becomes incredibly small, right? So we will be summing all of these areas from 1 to n, the number of rectangles that we have, and then we're going to take the limit of that as n tends to infinity, and that will give us precisely the exact area underneath the curve between those points. And that is the concept that is integration. Okay, so to determine the area underneath the curve between the points 0, 0 and 1, 1, we'll integrate between 0 and 1. So this is x equals 0 and x equals 1. The function is y equals x squared. And because the boundaries, the limit of integration, are x boundaries, we are integrating with respect to x. Now this should look familiar because we had earlier illustrated by rectangles delta x, right, which is the width of the rectangle. So this represents the width of each rectangle, and fxi represented the height, and fxi is the function x squared. So we'll be integrating x squared with respect to x. So that equals the integral of x squared is x cubed divided by 3, and that's evaluated between x equals 0 and x equals 1. So that will be 1 cubed over 3 minus 0 cubed over 3, which equals a third, which confirms our estimated guess when we were looking at the rectangles that the limit as n approaches infinity approaches a third, and this was the limit.